welcome. Today we're happy to give a warm welcome to Sean Trott. Sean is an assistant professor of psychology at Rutgers, Newark. He's brand new to Rutgers. He's coming to us from much warmer climes. He was at University of California, San Diego, where he earned his PhD in cognitive science, and he also served as assistant teaching professor for the past 4 years. That's about right.
Three,
right?
yeah.
Three.
Exactly, yeah.
We'll round up to 4. And his work uses large language models as really model organisms to study human language and cognition, while also applying methods from cognitive science to better understand how those models actually themselves work. A research program he sometimes refers to as LLMology. And that's basically what he's going to be speaking about today. So without further ado, let's give our attention to Sean.
Thank you so much. Thanks for the invitation. I'm really excited to be here and to talk about this work. So yeah, as you said, I'm Sean. I'm going to be talking today just sort of generally about some research I've been doing on language models and false belief representations or sensitivity to false beliefs. And just to kind of give you some context about the kind of research I do, I'm interested sort of at questions that lie at the intersection of cognitive science, questions about human cognition, and questions about this new technology, large language models. So as Sten was saying, some of my research uses language models, as you might think of as model organisms, to operationalize and test hypotheses that are really difficult or maybe just unethical to test in humans, and I'll say a little bit more about that in just a second. And then at the same time, we can apply these methods and theories that we've developed in psychology and cognitive science to better understand these systems that, although we know a lot about maybe how they're built, how they're trained, we actually don't understand a lot about how the internal mechanisms in these systems give rise to the behaviors that we observe, or even the best way to study and measure those behaviors. And increasingly in the last year or so, I've been interested in kind of the common set of epistemological foundations or background assumptions we bring to bear on both kind of sets of questions here, and also what are the limits or advantages of using LLMs in terms of model organisms to study human cognition. What kinds of inferences can we draw from them? What kinds of things can't we use these as model organisms for? So I'm going to talk a little bit about those kinds of questions in the talk as well. So just to kind of start off, humans ascribe mental states to other people, other agents, sometimes even inanimate objects. In some cases, many of you are probably familiar with this classic example showing people tending to ascribe, a whole narrative as sort of intentionality to shapes on a screen. We also reason about these mental states even when they're different from our own. There's obviously huge bodies of research on this capacity. Sometimes it gets called theory of mind, sometimes mentalizing. There's a related constellation of abilities and behaviors that we might generally say is the ability to reason about, make inferences about, use information about downstream, the mental states and emotional states of others. Seems central for social cognition, maybe even using and understanding language. And one really big question in this literature, of course, is where this capacity comes from in humans. And as is often the case, there are competing perspectives. Some perspectives emphasize the role of an innate, biologically evolved endowment. There are both kind of philosophical, theoretical, and also empirical reasons to think that might be the case if humans adapted in a very social context requiring lots of cooperation with others, coordination with others. It makes sense that there would have been a selection for some kind of innate construct in the brain that would perform something like social reasoning in this way. There's another perspective which emphasizes the role of experience. Although within this category of sort of experience-based perspectives, you can break it down into whether it's visual experience, social experience, experience with maybe language specifically. So within this category of the sort of experientialist hypothesis or empiricist hypothesis, there's an idea that maybe exposure to human language might augment or maybe even construct wholesale, depending on who's making the position, the ability to reason about the mental states of others. There's a few pieces of evidence that people sometimes cite in support of this view. So one is that there's a correlation between the age at which a lot of children start learning mental state verbs, so verbs about the mental states or belief states of others, know or believe or think, and when they start doing well on tasks canonically used to assess theory of mind or belief state reasoning. So that's correlational evidence, right? It's not causal, but it suggests maybe these things are starting to come online at similar times. There's also some evidence that learning certain kinds of syntactic structures, so sentential complement syntax. Mary said that Fred went to the movies, these embedded nested clauses. There's some experimental evidence, in fact, that training people on these kinds of structures improves their performance on false belief tasks. Again, it's a limited set of studies on this. There's not, we don't know to what extent it generalizes across lots of different kinds of syntax or different kinds of false belief tasks, but again, some corroborative evidence in support of this hypothesis. But as I said, a lot of the evidence is correlational, and it's really hard to isolate in humans, of course, a causal functional role for language. Because if we think, for example, about the mental state verb evidence, there's this correlation or link between these two things, but we don't know necessarily which direction this link goes. It's really hard to isolate that. It could be that children start learning mental state verbs, and that scaffolds their ability to acquire something like theory of mind. It could be that they learn those mental state verbs once they have theory of mind, because that's how they're able to learn the verbs, right? That having something like theory of mind gives them this sort of conceptual foundations to acquire those verbs. So it's really hard to isolate the effect of language exposure, independent from innate constraints, independent from social experience, independent from grounded experience in the world. Humans have all of those things, and so it's really hard to isolate any given one of them. And so ideally, you'd have some kind of model organism, a system that's exposed only to one of those things, maybe exposed only to language. And then you can ask what kinds of behaviors you observe in that system, and so which behaviors are at least in principle attributable to language. So I want to segue for just a second to talk about what a large language model is, just to make sure we're all kind of on the same page about what I'm talking about. So a large language model, or LLM, is a neural network with many parameters trained on text data using typically a next or mass token prediction paradigm. So just to kind of explain what I mean by that, if I show an LLM a sentence like, I like my coffee with cream and blank, this might be fed into an LM, which here is represented just as a large gray box. We're not going to peek under the hood of this box today, although I'm happy to talk about research on the mechanisms and so on. The LLM produces an output distribution, a probability distribution over the next likely token. And when that language model has just been initialized, right, it doesn't know anything about the statistics of language. A word like sugar might be equally as likely as a word like salt, which might be equally as likely as a word like dog. Now, the hope is that over lots and lots of training, lots of exposure to sentences like this one, the language model will learn that a word like sugar is more likely in this context than a word like salt, which is also more likely probably than a word like dog. So that's the basic idea, that the language model is basically trained on to do a kind of autocomplete, but with lots and lots of examples. And so now turning to this idea of using language models as model organisms, or what I call distributional baselines, right? Throughout lots of areas of science, people use model organisms to test questions that are very difficult or unethical to test in humans. And we always have to keep in mind, of course, a caveat that we're testing a model, not the thing itself. But in this case, some of the limitations of a language model we can actually kind of use to our advantage, because the fact that a language model is only trained on language, which is obviously very dissimilar to human experience, means that we can better understand the extent to which exposure to this particular kind of input scaffolds or helps construct particular kinds of behaviors. So because they don't come pre-wired with any kind of knowledge, right, an LM is, to some extent, some purposes, we can talk about some of the finer-grained questions you might have about this, but they're largely a blank slate in the sense that the architecture is completely randomly wired when it's first initialized, and it's only through training that you update those weights, and it's, in this case, training on language input specifically. So that makes them really useful distributional baselines, which is kind of a question about what effect on some language-based task, so it could be any language-based task, but we're going to be talking here about false belief tasks, could be attributed to distributional learning of language statistics. And again, there's a more general idea, even beyond research on theory of mind, that exposure to language maybe accounts for a lot of what we know about the world, both about language structure, about world knowledge, about maybe social knowledge. There's this idea that when you couple that with some kind of prediction mechanism, that maybe can account for a lot of the kinds of things that humans can do. And so now we actually have a system that we can use to put these questions to the test. So it's no longer purely hypothetical. We can start to ask, what actually do you see? How far can you get with such a system? And then an auxiliary benefit is sort of in the domain of LLMology, right? Being able to understand these systems better. So they can help us understand humans, hopefully, and using cognitive science techniques, we can better understand this kind of black box of a large language model. So a classic task for understanding theory of mind is called the false belief task. Many of you are probably familiar with it, but I'll give a brief description. The false belief task tests whether a participant is tracking another person's beliefs about the location of an object. This is just a kind of schematic of how this task often works, sometimes called the Sally-Ann task because of this example. Right, so Sally, and Anne are in a room. Sally puts a ball in the basket, goes away, moves the ball to her box. Sally comes back. Where's Sally going to look for her ball? Right? And if the participant's egocentric, right, they're not modeling what Sally knows about the situation, they might predict that Sally is going to look in the new or true location of the object because that's where the participant knows it is. If the participant's tracking Sally's beliefs, they should have been tracking the fact that Sally was not there when Anne moved the ball to the box. Hopefully they should predict that Sally will look in the original false location of the object. This is kind of one of the classic tasks. I want to point out that there is a lot of debate about whether this is the best test of theory of mind, whether there's known limitations of the task, but it is a fairly canonical task, so I thought it was a nice place to start for sort of getting traction of the question of whether language models are sensitive to false belief. Now, the canonical task is often done sort of visually or situationally when you're working with children. Language models, by their design, are of course operate over strings of text, so you need a written form of the task. And so what we did was we created 12 scenarios, basically, or passages, with a similar structure. Not exactly the same as the Sally-Ann task, but basically the idea is you have, in each case, 2 characters. There's a main character that places an object in some start location. The object gets moved to an end location with or without that first character's knowledge, so true belief or false belief conditions. And then you have a final sentence probing that character's knowledge state about the object, either explicitly, so X thinks that the ball is in the blank, or implicitly X looks in the blank for the ball. So that's what we called the knowledge queue. We also controlled for some things like which order the different locations were mentioned and the number of times each location was mentioned. So just to give you an example, Sean is reading a book. When he's done, he puts the book in the box and picks up a sweater from the basket. Then Anna comes into the room. And then there'd be 2 different continuations of this depending on the condition you're looking at. In the true belief condition, Sean watches Anna move the book from the box to the basket. Sean leaves to get something to eat in the kitchen. In the other condition, the false belief condition, Sean leaves to get something to eat in the kitchen while he's away. Anna moves the book from the box to the basket. So roughly the same set of events occur in each case. They just happen in a different order and with different characters being aware, basically, for those events happening. Now, in both conditions, we see a continuation. Sean comes back into the room, wants to read more of his book. Now, in the explicit condition, you would see a final probe that looks something like this. Sean thinks the book is in the blank. Or in the implicit condition, Sean looks for the book in the blank. So as I said, we had a number of different manipulations. So if we have 12 scenarios, 16 versions of each passage corresponding to the manipulation of knowledge state, this way that we probe what the language model or a person is modeling about the knowledge state of the character, which location was mentioned first and which location was mentioned most recently. These last 2 were basically to control for the fact that both language models and to some extent humans have some biases about the first location that might be mentioned and also the most recent thing that tends to get mentioned in a passage. And so for a language model, the way that you can assess this is because language models are designed to produce a probability distribution over the next token, the experiment has basically been designed such that we can look at the probability that that language model assigns to either the start or the end location in the context of the false belief or the true belief passage. So just to kind of show exactly what that might mean, if the final sentence we give, the language model is Sean looks for the book in the blank, it's basically a kind of closed task, like a completion task. It has to predict the next word. We can look directly at the probability the model assigns the word box or the probability that the model assigns the word basket. These correspond to the start and the end location in the passage. We can then calculate something called the log odds, which is the log of the ratio of these probabilities. So just to kind of illustrate what log odds will mean, if the start location was assigned a higher probability, this value will be positive, the log ratio will be positive. If the higher value is assigned to the end location, this ratio will be negative. So intuitively then, in the false belief condition, we might think that the person should look in the start location. So in the false belief condition, the log odds should be positive. in the true belief condition, the log odds should be negative. So now we have this metric, this variable that we can look at, that if a model is sensitive to false beliefs or this manipulation of belief states, this should vary systematically according with our experimental manipulation. And if it's not sensitive, right, then we shouldn't see that variance. So the first study we did, which is the first thing I'll be talking about, the published work in 2023, we applied this method to a particular model that at the time was sort of the best model. So GPT-3 was a model released by OpenAI. Text DaVinci 002 was just the specific name they gave to the model that was, at the time, the largest that had been trained on sort of the most data. I'll be talking right after this about some replications that we've done more recently on open weight models, but this is sort of the original stuff, just to kind of give you a sense of what we did. So what you see here on the x-axis is GPT-3's log odds. So remember, a more positive value on log odds means a higher probability was assigned to the start location. A more negative value means a higher probability was assigned to the end location. What you see also is broken up into the knowledge Q conditions, so whether we are probing knowledge states explicitly, like Sean thinks X, or implicitly, Sean goes to get the ball from the container, or whatever the scenario is. And then the most important thing is this manipulation of knowledge, right? So the red distribution is the distribution of log odds from the model for false belief passages. The blue distribution is the distribution for true belief passages. And we notice a couple of things. One is that the red distribution is sort of systematically to the right of the blue distribution. So on average, the model assigns a higher probability relatively to the start location than end location for false belief conditions, more so than true belief conditions. So in other words, this metric, this variable, varies systematically according to the manipulation. So it is, you'd say it's sensitive to this manipulation of knowledge state. You could kind of convert this to an accuracy measure. It's a little bit coarse-grained, but if you just take 0 and we say everything above 0 in the false belief condition is correct, everything below 0 in the true belief condition is correct, kind of you basically binarize according to saying, like, now it's a higher probability of start, or higher probability of end. That corresponds to an accuracy of about 74%. So it's better than chance. It's definitely sensitive to implied knowledge states. The other interesting thing that we didn't expect, which we'll just talk about briefly now, but also come back later, was this main effective knowledge Q. So you might notice that these two distributions here, the blue and the red distribution here, independent of this knowledge state manipulation, are much further to the left, much more negative than these two distributions over here. So in other words, when the model is probed with a knowledge Q probe like Sean thinks, this explicit probe, it is more likely to attribute false beliefs than when it is probed with this implicit probe. So in other words, when it's the verb thinks is used, the model is more likely to respond as if the person has the false belief than when an implicit probe is used. So we thought that was interesting. I will talk about that more in just a second, but I just wanted to note that. Now, of course, this is just behavior in the model. We wanted to know how this compares to human behavior on the same task because we created completely new stimuli. So we wanted to get sort of a human comparison point for those particular stimuli. So we recruited over 1,000 participants on Amazon Mechanical Turk. This is back in 2022 that we ran this study. Each participant read a passage on a new page. They were asked to complete the critical sentence. So we kind of wanted to match as closely as possible the sort of thing that GPT-3 was being asked to do, which is kind of a closed task. We didn't want participants to learn that they were supposed to be paying attention to this information because we didn't tell the language model to pay attention to this information. For that reason, this was a single trial experiment. So every participant just saw a single passage. We also had quite a few participants that we had to exclude according to pre-registered attention checks. So we had a few different attention checks. One was just checking whether they could accurately report the original location of the item and also the end location of the item. And then the other thing was people who answered with something other than the start or end location. So this actually was a huge volume of people, almost half of the participants. It's worth noting that if you keep these people in, the human average just goes way down, right? So these are people that presumably weren't really reading the passage very carefully. They couldn't even report the basic location of the item. If you keep them in the human sample, then human average baseline is going to go down to about, I think, 53%. So I think there's a strong case to exclude them just because we don't want to be sort of including people that aren't paying attention at all in the sample. But notable, perhaps, just in general for running online studies that so many participants had to be excluded for this reason. So we have two questions. One is, of course, just whether humans show an effective knowledge state we expect them to. These are all adult humans. We should expect them to show this effect, but we just want to sort of see what that effect size is. And then the more sort of relevant question is, does the performance or does the behavior of a language model on the task sort of explain away that effect? So if you think of this from a statistical modeling example, like if you're trying to predict human behavior, like the human choice on a task, you could put that in a linear mixed effects model, predict that from log odds from GPT-3, as well as your experimental condition. Now we expect experimental condition to significantly predict that output variable. But once you include log odds in the model, does that basically account for the same variance statistically that condition was previously accounting for? So in other words, does knowing about the language model's performance or behavior on an item basically tell you as much as knowing the experimental manipulation? This is a way of thinking about to what extent can you statistically account for the human effect through sort of distributional statistics. It doesn't mean that's what people are doing, it just sort of provides statistical corroboration for the idea. So here's sort of transforming human responses into a more continuous probability distribution, sort of aggregating across humans to basically tell you in the false belief condition, what was the distribution by item in the false belief condition versus true belief condition of start responses versus GPT-3. And we see that, again, as we already saw with GPT-3, there's some effect, but it's much larger in humans. It also seems like much more categorical in humans. If you look at just raw human accuracy, it's about 83%. So not at ceiling, which is also notable. There were humans who passed the intention checks, but did not pass this particular task. That seems worthwhile to note. But the effect of GPT-3 log odds did not really even come close to explaining away that effect, right? So there's a sizable gap between the sensitivity we observed in GPT-3 and the sensitivity to false belief we observed in humans. So just to kind of wrap up that first study, GPT-3 did display sensitivity to these manipulations of knowledge states, but still considerably below human performance on the task. So if we think about the original question as being, are language statistics sufficient to account for human behavior on this task, we'd say, according at least to this operationalization, the answer is no, right? It's sufficient for some sensitivity, but not human level sensitivity. One really key limitation with this work is that GPT-3, the model we use, was what's called a closed source model. So we don't know actually anything about the data that GPT-3 was trained on. We don't know the weights in the model. Now, there's a number of problems with using closed source models. One is it raises concerns about data contamination. So if a model was trained on the same examples that you're testing it on, that's obviously an example where they may not mean the same thing anymore, right? They're not really a valid test. Now, we are pretty confident, or very confident that shouldn't be the case because we created entirely new stimuli, but there's still just general problems of reproducibility. So GPT-3 notably has now been deprecated. So you can't replicate this experiment that we ran, unfortunately, because OpenAI no longer offers the same access to the individual probabilities that GPT-3 used to give you. So that's unfortunate. We wanted to have research that is replicable by other researchers in the field. There's also just questions about if you have a single model, to what extent does that sort of give you generalizable claims about a larger class of models? So to address this, more recently in unpublished work, we replicated this result with 41 open weight models from 5 different model families. So model families are kind of like a class of models trained by the same provider. Open weight models, many of these were also open source, meaning we have actually like the raw source code and data that the model was trained on. So we can ask then, do any of those models, they ranged in size and architecture, training data amount, do they show sensitivity to implied belief states? Do any of them explain away the human effect? And then the other advantage of testing a larger sample rather than an N of 1 essentially is that we can start to ask about statistical regularities in that sample. So you can say, do some models show a larger effect than others? What predicts that variance in effect size across models? Can that tell us things that we can conclude more generally about language models? So I'll just show you on the x-axis here is the number of parameters in the model. So that's just the number of weights, basically, so the size of the model. Bigger model generally tends to do better on different tasks. On the y-axis, we have accuracy on this task, which remember is basically positive responses in positive log odds in the false belief and negative log odds in the true belief. Each of these dots is a model. The circles are what's called base models. This is something I haven't really talked a whole lot about. It's not super relevant to the point I want to make, but base models basically means it's just trained to predict the next word. These instruction-tuned models are trained with an additional training objective after that initial training to basically follow instructions. There's some evidence that instruction tuning helps with writing code, with some other kinds of tasks that people like to use these models for. So we wanted to also look at whether the kind of training regime it got affected its performance. And then the orange line here is the human baseline from that 2023 study. So first of all, we wanted to ask, are any of these models sensitive? And we see that after you correct for multiple comparisons, because we're looking at 41 models, 14 of those models that we tested were significantly sensitive to implied belief states. So there is a non-trivial subset of that sample that was sensitive. And as you can also see pretty clearly, bigger models here show bigger effects. It's not a perfectly linear effect. This is also a log scale, notably, but it's also not. It's both not linear and not perfectly monotonic. So there are models that are smaller than other models that nonetheless do better than this model. So it's not like you have this perfectly linear thing where if you're a bigger model, you're going to do better on the task. We also have another analysis looking at the amount of training data each model saw. In this case, that actually wasn't predictive once you accounted for the size of the model. But if you don't look at the size of the model, the amount of training data does predict it. So when you know both factors, the number of parameters is the most useful thing to know about. There, in this case, also wasn't an effect of the kind of training that the model got. The best model was a model out of Allen AI called OLMO2. It's a sort of totally open language model, which is really great because it means that we can run data audits. We can look at the kinds of data that it's trained on. We, along with some collaborators, have done that to verify that our stimuli weren't, in fact, in the training data, which they weren't, which is good. And the best model got about 74%, so pretty comparable to what GPT-3 got on those same stimuli, interestingly. Now, remember our key question here was, do these account for human behavior? And none of them attain the human baseline, and no model statistically explained away the human effect on that same task. Now, I want to contrast this with something else, which is something I mentioned earlier, this knowledge queue effect. So remember I mentioned that GPT-3, as well as actually all these open weight models, showed this effect of the way that we are probing knowledge state. So when the model was probed with a question explicitly about a knowledge state using a non-factor verb, he thinks, versus this more sort of implicit probe, like he goes to get, they tended to attribute more false beliefs. So they responded as if the character would behave with a false belief. Now, one possible explanation thinking about this is that with some non-factor verbs like thinks, there's some semantic theories or pragmatic theories suggesting that there's kind of an implied anti-presupposition. So if you say something like he thinks this, it's not like entailed that X is wrong, but it might be sort of weakly implied, right? And so maybe that's something that a language model could pick up on distributionally as well. Maybe distributionally, when you encounter constructions like he thinks X, X tends to be something that is a false belief more so statistically. Now, that would still be interesting for a language model to have picked up on that. We wanted to ask whether humans also show the same effect as well, because this wasn't something we expected going in, but we wanted to ask whether humans showed this effect on the same study. So we do actually see humans see the same effect, and what we did was calculate an effect size for each model and also for humans. So the way we're visualizing this is the difference in proportion of start responses across conditions. So what that means is basically the tendency to attribute false beliefs in each condition, in this case explicit versus implicit, and the difference between those. So a positive value means the greater extent to which you're more likely to say that someone has a false belief in the explicit than implicit probe. So the further to the right you are here, it means like you show a bigger effect of that knowledge cube. Each of these parts of the histogram is one of the language models that we tested. Remember, there are 41 of them. The dashed blue line is just the mean of that distribution, and then the solid red line is the human effect. So the human effect was actually pretty comparable to the mean of the LLM distribution. One sort of conclusion you might draw from this is that if the average human effect size here is about comparable to the average LLM effect size across a range of LLM sizes and so on, that suggests that in principle, again, not necessarily, but in principle, exposure to sort of distributional statistics could account for this kind of human effect. What I like about this is two reasons. One, I think it's interesting because we were able to sort of generate this hypothesis not sort of a priori, right? We didn't design the experiment to test this. This was something that sort of came out from looking at language model behavior. So there's a lot of interest right now in using language models to generate new hypotheses you can go back and test in humans. Maybe this could be a nice example of that. But I think the other reason it's sort of a good example here is that it's a nice contrast to the effective knowledge state. So if you do the same thing, but you look at the difference across our main manipulation, the false belief versus true belief condition, again, you look at the distribution of effect sizes across those conditions versus the human effect size, we see a very different pattern, which is, again, the LLMs have this kind of right-skewed distribution. Some LLMs show bigger sensitivity than others, but the mean is sort of right about 0.2. Humans are way over here to the right. So unlike the knowledge Q effect, where humans are kind of squarely in the middle of the LLM distribution, the manipulation of knowledge state, humans are much larger effect than the distribution of LLMs. So this is a nice contrast because it says that it's not that you're just always going to necessarily end up with this. It's not like a weird artifact of the analysis we're doing necessarily. There are going to be some effects possibly where the LLM distribution does kind of statistically account for the human effect, just in this case not this manipulation of knowledge state. So sensitivity to false beliefs is much greater in this case than humans than in the language models. So just to wrap up where we stand so far, in this written false belief task, right, about a third of our sample of language models that we tested did show some sensitivity to our manipulation of belief states. Bigger models tended to do better when they're trained, especially when they're trained on more data. But no model reached or surpassed the human baseline. So this suggests that sort of training on distributional statistics of language might be sufficient to account for some sensitivity to knowledge states, but still not really at the human level, right? So there's an interesting question there that arises about, what accounts for that gap, right? Could that be grounding? Could it be sort of in-person social interaction? Could it be dialogue? Could it be innate constraints, right? As I said, these models are initialized with a totally homogeneous architecture that hasn't been subject to biological evolution. What are the various factors that account for that gap? Is it just training on even more data? We just have to make even bigger models. There's any number of different explanations you might have. There's also some important constraints on the finding, which is that these models are trained on orders of magnitude more text than humans are. This will be relevant in just a minute when I talk about assessing sort of theory of mind more broadly in language models. Now, in this case, I don't actually think that affects our inference because even with that difference, even with that order of magnitude difference, they still don't get to the human effect. But if they had surpassed the human baseline, that would be an important point to bring up, which is that they are trained on orders of magnitude more text. In this case, it actually kind of works against the model in the sense that you might say even with that effect or even with that difference, they still don't account for the human effect size. But I think another question that comes up here is it's not totally inconceivable, given how these models are doing, that at some point they're going to perform as well as the average human on one of these tasks, or average participant in one of these tasks. It's going to depend on the sample. You might have qualms about whether you wanted to surpass the human average or whether it should get 100%, but at some point it's not inconceivable that it would do so. And so I think that raises a really separate important question about what it even means to conclude that such a system would or would not have theory of mind. And so I think there's kind of three different interpretive views you might adopt here, and they all kind of have to do with your view on the relationship between a measure and the construct that that measure was designed to assess. So there's what I call the duck test view, which is kind of a very straightforward approach which says, if it walks like a duck, it quacks like a duck, and so on, it is a duck. If a system passes the false belief task and we think the false belief task is a measure of theory of mind, then we would draw whatever the same conclusions we draw for a human. That system has theory of mind in a relatively straightforward way. There's what I call the axiomatic rejection view. So this view says there is something that LLMs lack, either because of their architecture, because of the way they are trained, that says that a priori we're going to say that they cannot have theory of mind. It's not about their performance on the task. In some sense, we don't actually care about how they perform on the task. By definition, it's just sort of a category error to say that they could have something like theory of mind. There's some philosophical reasons you might say something like this. Maybe if you don't think LLMs can have beliefs, then they can't have beliefs about beliefs. Now, interestingly, both of these views have somewhat radical consequences. So if you take the duck test view and a model passes the false belief task, then you're kind of forced to conclude that it has theory of mind, which feels like a somewhat radical conclusion about a language model. If you take the axiomatic rejection view, now you're in a situation where a model that has been declared to not be capable of having theory of mind is performing well in a test that is designed to assess theory of mind. So it's almost kind of like a reductio of the test, right? It suggests that it may not be a good test of theory of mind if it's saying that something has theory of mind that you don't think should. And so there's kind of a third view which tries to navigate between the sort of consequences of these views, which I call the differential construct validity view, which broadly says, the same test doesn't necessarily mean the same thing for different systems. And this, of course, is actually not that surprising, right? There are lots of different routes by which the same behavior could be produced in different systems. Some of those routes might correspond to the same construct, some of them may not. Some of them might be what we might think was like a shortcut or a heuristic. Other ones might be sort of the correct way to solve a task. Now, I think there's a general intuitive appeal for a lot of people, including myself, to this differential construct validity view. Not least because you can sort of avoid either of the unfortunate radical consequences of these things, these other views. But actually kind of trying to articulate what exactly it means and why is, I think, much harder. And so over the last year or so, I've been thinking a lot about this particular question of when and why would a test have differential construct validity? Can we actually articulate a series of principles as to when we should say that the test does have differential construct validity, rather than just saying, oh, it doesn't mean the same thing? Can we say why it doesn't mean the same thing? And is there actually a way that we could devise an empirical investigation into that construct? Or is that not really on the table? Is that hopeless? And so sort of broadly, the way I'm thinking about this is to dividing this into theoretical and empirical perspectives. Theoretically, you can ask a couple questions, which is just, first, is it a priori plausible at all that a system like a language model could have theory of mind? If you think the answer is no, then maybe it's not really worth investigating the rest of these things because you're basically already kind of in the axiomatic rejection camp that I mentioned already. But if you think the answer is yes, that it's plausible, but you need to actually look into it, you still have to answer this other theoretical question, which is, do the theory of mind tasks that we've developed for humans have sort of the same face validity for LMs? Does it make sense even just sort of, not from an empirical perspective, just kind of at face value, intuitively, to use them for language models? And then empirically, there's all the ways that we assess construct validity and test validity in humans. One is convergent validity. So typically, if you want to ask whether a new scale, a new measuring instrument is a good measure of something, you ask whether it correlates with other measures of that same thing. There are a number of different tasks that have been devised to assess theory of mind. You would hope that they should show some degree of convergent validity in LMs if you think they're all tapping into the same construct, rather than completely different sort of mechanisms or capacities. And then finally, what I've been calling sort of process and mechanistic validity, which is if you actually break down what the LM is doing to solve the task, does it have the right sort of preconditions? Does it solve other tasks that you think should be necessary for theory of mind? If you look at the internal representations of the language model, and you try to put together kind of a mechanistic account of how it's solving the task, does it actually map onto our sense of what a theory of mind consistent behavior would be? So I'm going to try to work through these one by one and talk about some of the research I've been doing on each of these points. So the first thing is, is theory of mind plausible at all in language models? Now, this is something where I think there's going to be a lot of different opinions in general. People have very different priors on this question, basically, that I want to try to make the case in both directions. One is the case that it's implausible, right? So LLMs, as we know, are next token predictors. Many of them are trained on text alone. Now, if you think that theory of mind requires intent, understanding communicative intent, having a capacity for belief, maybe you think it requires grounded social interaction. If you also think that LLMs don't have any of those things, which plenty of people don't think, then you might conclude that a priori it doesn't make sense to say that they would have theory of mind. So I think the case against it is not particularly hard to make. Now, the case that theory of mind is plausible actually starts from the same position, which is that learning to predict tokens is what language models are trained to do. But maybe it is the case that this training objective requires them to learn to encode information that is present in the tokens in a distribution that aids the prediction even better. That could be any number of things. It could be grammar. It could be basic facts about the world. It could be properties of the agents described in text, including the mental states of those characters. There's a number of people that made variants of this argument over the last few years. namely that you don't want to conflate the training objective with the sort of emergent capacities of the system. It seems in principle possible that a system trained to do this apparently simple thing, right, predicting tokens, could learn, given the complexity of the system, more rich representations that would allow it to do things that are sort of not explicitly designed into the system from the beginning. So we might call this, theory of mind light, right? It's not going to be what we think of as sort of the rich complexity of theory of mind in humans, but it's sort of the narrow capacity to encode in the internal states of the model information about the mental states of characters in a passage, infer those states, and use that information to make predictions about what those characters are going to do. And so that's the kind of version of theory of mind light that I'm going to make the case is sort of, I think, not unreasonable, right? So if we take that at face value, which not everyone might, then we can proceed to the next question, right? Which is, do these theory of mind tasks actually have face validity for LLMs? Now, theory of mind tasks, like the false belief task, were developed to assess humans' ability to infer belief states and deploy that knowledge to predict behavior downstream, right? So to solve the false belief test, you have to be tracking, the likely mental states of Sally in the situation, and then you have to use that information to predict what Sally is going to do. And as is the case for many different psychological constructs, right, we have this construct that we want to get at, but we can't directly observe it, right? Theory of mind is not a thing that we can point to or observe. What we do have is a measure, which is false belief task performance. And the false belief task is designed to sort of reify the sort of relevant parameters of this construct, we hope. And we assume that there's some kind of generative or causal link between this latent construct that we can't observe and behavior on the task. That's kind of generally the inferential logic. And thus, variance in false belief task performance, we can draw this inference about variance in theory of mind. That's the logic when we use this for humans. So the question is, does this hold for language models? And I think there's a few challenges here to arguing that it does. And one is this problem that I brought up earlier, which is that language models observe orders of magnitude more text than humans, including false belief task examples. Like, it's almost certain that there will be examples of the false belief task, descriptions of the false belief task, descriptions of theory of mind in a language model's training data. Those things are all going to be in Wikipedia. They won't have seen the specific examples we used or someone else might have used, but it will not be ignorant of the idea of theory of mind. It will have been trained on that. That is, of course, very different than when you're testing a child or even an adult on the theory of mind tasks, like the false belief task. Maybe, if someone in this room, they've taken classes on theory of mind, but for the most part, people are not going to be that familiar with the false belief task, right? And so there's a difference between humans and LMs in the relationship between their experiences and the task itself. And I think that is sort of one area where differential construct validity starts to creep in. Because the fact that the LMs have seen these similar examples of the false belief task provides another kind of generative or causal account by which behavior on the false belief task could be produced, right? With humans, we think there's this sort of direct link between theory of mind and false belief task performance. In the LMs, the problem is maybe the false belief task performance could be from theory of mind, but maybe it's from the fact that they saw very similar examples in their training data. And this raises another question, which is sort of what really counts as generalization, right? Even if you can rule out verbatim data contamination, like this model saw exactly these stimuli in its training data, how different do they need to be from what it's seen as training data to constitute like an interesting form of generalization? I don't think we have a formal answer to this question. I'm not sure that we can, right? There are ways in sort of simpler distributions of saying this is in distribution or out of distribution. With something like theory of mind, I think the construct is so abstract that it'd be really hard to formalize it in that way. But we might have the intuition that giving a language model an example of theory of mind with Sally and Anne and then just swapping the names isn't really sufficient, right? That seems like something a language model could learn to solve without requiring theory of mind. It could learn to pattern match in a way that doesn't require it to develop the capacity for mental state reasoning. So just swapping the names isn't enough. What about swapping the location, the items? How many parameters have to be different? Or would it be better just to not have examples of it at all in the training data? Maybe have train on child-directed speech or something like that. Have a conversation transcripts that is trained on. So these are all, what I would argue, very open questions, things I'm interested in trying to answer. And they all have to do with the relationship between the data on which a system is trained, the exemplars that it sees, and the kinds of things that it is being tested on. But I think in the context of the case I'm making for differential construct validity, I think what we might want to argue is that theory of mind tasks, while they're not necessarily invalid for language models, we should in general demand a much higher standard of evidence for drawing inferences about theory of minds and LMs. We shouldn't just say that just because this task is valid in humans, or we think it's valid in humans, that we can draw exactly the same inferences. I think a good reason for that is just this difference in the magnitude and type of training data that they see. So where does that leave us? Well, maybe we think it's somewhat plausible, but we don't think we can just draw exactly the same inferences from our task. So now we have to move on to the sort of empirical approach, where we try to build this higher standard of evidence and see whether they meet that higher standard of evidence. One higher standard of evidence might be convergent validity. So this is some work I did with Cameron Jones and Ben Bergen, developing basically not just one task, but a suite of theory of mind tasks using examples from the literature on theory of mind, and relying on this idea of convergent validity, right? If different tasks mean the same thing, then if they are all measuring the same thing, then behavior on those tasks should correlate with each other. So if we think no single task is going to provide sufficient evidence for a language model theory of mind, maybe we can still establish convergent validity across a diverse range of tasks. And that is what we call epitome, experimental protocol inventory for theory of mind evaluation. And so I'll just really quickly talk about some of these tasks, and I'm happy to give a lot more detail in the Q&A as well. But one of them is the task you already saw, the false belief task. One of them is this recursive mind reading task. So this comes from a cognition paper from 2015. Some of you might be familiar with it. Looking at basically how many levels of embedding people can draw mental state inferences about. And it was a paper that I was really surprised by when I saw the finding, because the claim was that people can actually attend about 7 levels of embedding about mental states. So these are people read dialogues. There's a dialogue version. There's also a story version, where and then you'd be tested on things like John thinks Sheila hasn't realized that he likes her. But you could imagine having 7 levels of embedding there. They actually had a control task, which was just sort of spatial descriptions, like the house that is to the left, to the right of this other house, and so on. And people didn't do as well in that control test. So there's actually a claim that there's something specific about theory of mind that might be particularly well adapted for these sort of very recursive embedded representations. So we, in the process, replicated this finding. I can tell you now, humans do actually still show the effect. So I was surprised by this, and it was nice to see this replicate. The humans did show roughly about 7 levels of embedding on these recursive tasks. We then used 2 different free response tasks. So the short story task is a 2013 task from Dodell Feder et al. Using a short story from Ernest Hemingway called The End of Something. Just to maybe some spoilers from the story, it's about a couple rowing their boat on a lake. They get in an argument and then they end up breaking up. But it's sort of implicit. So it's a Hemingway story. There's a lot of sort of like things aren't necessarily direct. And then you get asked a series of questions about why did this character say this thing? Why did they act in this way? Along with some basic kind of reading comprehension or like event knowledge questions. And basically the idea is they're looking to see to what extent people are drawing on kind of mental state knowledge when they answer these questions about why characters did what they did. So this is just another kind of data point. The strange stories task is also often used to look at sort of pragmatic, but also theory of mind capacities. They involve different things happening, again, in these kind of unusual situations, like Peter thinks Aunt Jane's hat is very ugly indeed, but when Aunt Jane asks Peter, how do you like my new hat? Peter says, oh, it's very nice. Why does Peter say that? They have a rubric to look at what the correct response should be, like he's wanting to express her feelings in this case. And then we had 2 tasks that were basically a combination of mental state reasoning and pragmatic inference. So one of them comes from a study I did back in 2020 with my PhD advisor, where each scenario describes like an interaction you're having with another person. Like you and Jonathan are in a car, you notice a blinking light, which indicates the car's heating system is broken. And then Jonathan produces an utterance which, under many circumstances, could be construed as an indirect request, like, man, it's really cold in here. And the manipulation is whether the character speaking knows or doesn't know about an obstacle to fulfilling that request. So it's kind of a standard false belief task in that we manipulate whether they know something about the world. But what we ask is whether knowing that about the world affects your interpretation of what they meant by what they said. So So it's kind of sort of multiple things that a person has to do. They have to draw this inference about what the person knows, and then they have to use that information to infer whether they were making a request to do something. The scalar implicature task is kind of a similar idea, relying on this idea of scalar implicature. This comes from a Goodman and Strohmiller paper in 2013. Looking at, and the example actually given isn't, so they have a few different manipulations, but the example given has sort of the sum, classic sum example. Like some of the pizzas have cheese in the crust. Does that mean all of the pizzas have cheese in the crust? Does it mean some, but not all of the pizzas have cheese in the crust? And what does the person's plausible mental state or knowledge state about the pizzas and whether they have cheese in the crust influence about your interpretation of some? And what they find is that when people think that the character doesn't have sort of complete knowledge versus when they do have complete knowledge, they draw different inferences about what they mean when they say some. So they draw different scalar implicatures depending on the knowledge state. So 6 different tasks, sort of 2 sort of more standard like false belief tasks, 2 kind of like reading and responding to stories, and then 2 tasks that require mental state reasoning and sort of pragmatic inference. So what I'll show you is just the right, so we obtained a human baseline for each task, and then at the time ran them all in GPT-3, and then again more recently in open-weight models. So I'll go ahead and show you just the original results for GPT-3 and the humans. This is the false belief, recursive mind reading, short story, strange story, indirect request, and then 2 of the different scale implicature tasks. So the violin plots is just the distribution of human performance. The dot with the error bar here is the average human performance with the standard error. And then the red diamonds is GPT-3's performance in each case. So for the false belief and recursive mentalizing task, GPT-3, as we already saw, was better than chance, actually in both cases, but fell short of the human baseline. So that's kind of consistent with the original study I mentioned. In the free response task, interestingly, GPT-3 actually did better than the human baseline for the short story task. It sort of got about the same level as the human baseline in the strange stories task. There's a few possible confounds for the short story task specifically, which is that GPT-3 tended to write more than most of the humans did because there's a free response task. A lot of people might just give very short responses. We try to control for that by then limiting it to, if you look at the subset of people who got perfect reading comprehension scores, what was their average, it was still a little bit below GPT-3's average, but a little more comparable. So the gap you see here might be a little bit smaller in practice once you do some controls. And then finally, on pragmatic reasoning tasks, GPT-3 was very, very bad. So basically either a chance or was basically a chance depending on what chance means in that task. And so that was interesting to us because we didn't necessarily go in with this hypothesis ahead of time, but it maybe is consistent with the idea that GPT-3 or language models in general struggle with pragmatic reasoning. Now, there is independent evidence collected by other researchers around the same time on pragmatic reasoning tasks, not necessarily mental state and pragmatic reasoning tasks, that these models aren't actually that bad, specifically indirect request and stuff like that. So one maybe tentative explanation is that these tasks sort of require multiple cognitive operations. Right, as I said, you have to infer information about a character's mental state, maintain that sort of in working memory as you're reading the passage, and then deploy that downstream when you're asked about what a character means by what they say. So that was one kind of tentative conclusion, but that obviously requires a lot of further research to look. But of course, just as we saw with the original false belief task, this was with closed source models. So we wanted to replicate this. We ran the same task on, sorry, that should say, I think 41 open-weight models, not 36. We added a few attention checks actually as well because we wanted to see to what extent the models were just sort of attending to basic information in the false belief passage. We also ran a new false belief task using the stimuli for that indirect request task I mentioned, just to see to what extent you saw convergence between these different tasks. Now, one of the benefits of running this with more models is that rather than just looking at how GPT-3 does on each task, you can look at correlations between each task because you have a distribution of model performances. So you can ask whether the distribution of model performances on the false belief task, for example, predicts the distribution of performance on the indirect request task, for example. Okay, so I'll show you first for each of the tasks that we looked at. You see model family. We also see the average performance of those models, and then each of the individual models are each of the individual dots. Arguably, the average doesn't actually mean that much because these are models ranging from like 14 million parameters to 30 billion parameters, but we have it just if you want to see the sort of mean of the distribution. We also have these red diamonds representing GPT-3's performance. So, and then the dots with the errors showing the human performance on that task. So there's a few sort of things of note here. One is that the average performance of these models was generally on par with or below GPT-3 and humans. So on average, this sample of models was not quite as good. But there were select models, like Quen 2.5 and some other models like Olmo, that actually outperformed humans in some tasks, or actually in general did pretty well. The most notable one is probably the indirect request task, because that's something that we saw GPT-3 perform so poorly on. This suggests that maybe our conclusion was maybe not correct, right? That there's not something inherent in the task that means that a language model can't solve it. This model does quite well. In general, though, if you recall across all these tasks, which may not be advisable, humans on average do quite better than any of the models. There really wasn't one model that did consistently really, really well across all the tasks. So the model that did best on the false belief task was not necessarily the model that did best on the indirect request task. That already kind of speaks to this question of convergent validity. But you can also just look directly at the correlation between each pair of tasks. So without sort of diving too much into the weeds here, we see here correlation matrix looking at the correlation between first the scale and implicature task, recursive mind reading task, and so on. And in general, we do see positive correlations between pairs of tasks for theory of mind, though not across the board. So for example, the indirect request task doesn't really correlate with performance on the other mentalizing task. The other thing to note is these, so this A1, A3, A2, A4, these are the 4 attention checks. The 3 of those attention checks correlate relatively well with each other. If you include even the one that doesn't correlate as well, the intercorrelation between those tasks is about 0.2, so not high by any means, but if you compare that to the correlation between the theory of mind task, that's about 0.08, which is very low. So I would say that in terms of sort of assessing convergent validity, there's some correlation, but it's really not that robust. So going back to sort of this question here, I think the limited convergent validity at best, I would say, between these different tasks. Now, that doesn't mean that what a language model is doing in any particular task isn't, mental state reasoning for that task, but it does suggest that at least for these language models, they aren't all tapping into the same generative process. It's worth noting that we don't have this data for humans, so we have a human baseline in each task, but we don't have human measures for all the tasks combined. It would be kind of difficult to collect for all the tasks that we ran, but it's something we've talked about doing to move forward as well. Because I think that would be really valuable to know as well, just generally for the theory of mind literature. And then the final thing that I want to talk about is this kind of question of mechanistic validity. So if you think about what the false belief task might reflect, if we think that a language model is using theory of mind to solve that task, the language model should also probably display some other set of preconditions. So for example, if you're going to represent the belief states of characters in a passage, it seems like that would benefit from a basic situation model of the passage, right? Put another way, right? If you're going to report beliefs about the locations of items, you should probably also know the locations of items. If you somehow are able to report beliefs about those items, but not the locations of the items themselves, it's not that that's a totally inconceivable thing that could happen, but it at least for me would make me think that the model doesn't have a very coherent representation of the situation. It might also decrease my belief that the model is really accurately doing mental state reasoning as opposed to some other kind of heuristic that I might be using. So we can then actually think about the different attention checks that we use. So where was the item originally? Who put it there? Where did the item end up? And who moved that item to that last location? These are sort of the 4 attention check questions that we ask. 2 questions about the location of the item, and 2 questions about who moved the item in each case. And so we can ask first, does a language model that does well in the false belief task, does it do at least as well on these kind of preconditions? And then we can also ask developmentally, sort of over the course of training, does a language model start to do better on these kinds of things before it starts to do well on false belief task? Because you would again expect if these are preconditions, then you should see a kind of series of training dynamics whereby first the model gets good at these sort of preconditions and then gets better at other stuff. right? So is that at least as good as these attention checks, and does that predict its performance? So what I'll show you here is each of the attention checks. So the item was first in the start, the item ended up here, who originally moved the item, and who moved the item to the final location. So you see the accuracy on the intention check question on the x-axis in each case, and the accuracy on the false belief task on the y-axis. So let's just look at the top left-hand corner just to simplify this at first. If these were sort of perfectly correlated, then you just see like a line of parity here. So the fact that these are all to the right of the line is sort of good in the sense for language model coherence, in the sense that if a language model does some accuracy on the false belief task, it tends to do just at least as well on the situation model task, on this particular question. So the language models are at least as good, generally better at reporting where the item started out as they are about reporting where a character believes the item is one way to think about that. That was mostly true for the other attention check question about item location, though there are some models that actually do better on the false belief task than answering questions about where the item actually was at the end. So again, concretely what that means is they are better at answering, where Sally is going to look for the item than where the item actually is. So that seems a little surprising, but most of the models, were also consistent in that case too. It's also worth noting that the R squared in these regressions was relatively high. So knowing how a model did on this attention check explained about 30% to 40% of the variance in how it's going to do in the false belief task. So they're pretty well correlated. But we see a pretty different pattern when we look at questions about agent actions, which was surprising. So models were actually really bad, often, in some cases like terrible, at answering who originally put the item somewhere. So if you have the Sally Ann task, Sally puts the ball in the box, and then Ann moves it to the basket. We ask who put the ball in the box originally, and it says Ann. It has a bias towards responding with the second mover in the passage. It never said Sally. Most of the models had this very strong bias towards responding with the second person. We see generally better performance on questions about who moved the item from the start to the end location, but still kind of mixed responses, such that there are some models that do better on the false belief task than they do on this attention check. So for questions about item location, most models are pretty good. Performance was a lot more mixed for questions about agent actions. And again, questions about item location were also much more predictive about performance on the false belief task. So again, we kind of have a mixed result in terms of coherence. I would say that relatively coherent in terms of tracking item locations and then beliefs about item locations, but relatively incoherent in terms of tracking the identity of people that move those items, which does feel relevant to sort of correctly solving the false belief task, because it matters that it was Ann and not Sally, or Sally that not Ann that put something there, because that's going to affect who you think knows what about the situation. Right, so mixed evidence. Now we can ask, do these abilities display an appropriate developmental trajectory? So do they come online in sort of the appropriate sequence, such that a model doesn't get good at the false belief task before it gets good at these basic questions about situation models? Now here we really benefited from the fact that the Allen AI Institute up in Seattle has released not only the final version of these models, but in many cases publicly available track points. So that means that we can look at how the model changes its behavior over the course of training, roughly how long it takes for the model to sort of reach like a stable point in its behavior, how good it is at different points in training, and how good it is at other tasks as well. So what I'll show you first is performance on these item locations, and I have superimposed the false belief task performance, and then also the relevant attention check performance. And that's in green and gray. On the x-axis in each case is the number of tokens seen on the log scale. That's just one way to sort of visualize the trajectory of training. This is probably just an initial bias, right? The model has an initial bias towards the end location versus the start location for responding to things. We see that just focusing on false belief, it takes a pretty long time. We actually do have measures from many of these points, but it takes a very long time for it to start improving. We see a bit of up and down. Pretty close to the end of its initial pre-training is when we actually see some amount of stabilization. If you look at additional post-training, it sort of remains relatively stable at about 68, and then eventually goes up to 74%. So that's the false belief task. Crucially, we do see jumps in performance in the situation model task generally before we see increases in the false belief task. So as we already established, right, these things are correlated, but they're also developmentally sort of happening in sort of hopefully the appropriate sequence. It would be strange if the model got really good at predicting where someone thinks something is before they can just accurately report where that item actually is. But we see that these happen in a relatively sensible direction. Things were a little more complicated for the agent actions. So we do see, some sort of sensible sequentiality here for the question of like, and moving the ball from the box to the basket. That the model tends to get good at that before it gets good at the false belief task. But it does very poorly, and as we already saw, on this original person question, and it sort of changes all over the place. So it's very hard to say anything sort of strong or concrete about this because the performance is so bad that it's not clear that it matters that it does better before or worse, right? The development doesn't actually tell us quite as much. So the performance is very bad for reporting the original mover. Reporting the person who moved the object does precede the false belief task performance improvement. So again, I would say there's kind of a mixed bag. Reporting where an item is and who moved it last does precede and also predict to some extent reporting where someone believes it is for these language models, but reporting the original character does not. So in terms of whether it has the right preconditions, I would say it has some of them, not all of them. I think an important question moving forward is what kinds of actual internal mechanisms observe these behaviors? Because there's a growing body of research generally called mechanistic interpretability or just interpretability, trying to figure out, because we do have access to these internal representations or internal weights of the model, can you figure out if there's a part of the model that seems consistently involved in solving this task? That would be one way to sort of establish that the thing that it's doing on each particular item, in each particular example, sort of recruits a similar portion or component of the model. And if you can knock out that component, right, do a standard ablation study, that if that knocks out performance on the task, now maybe you've identified a functionally involved region of the language model. This is a standard approach, obviously, in neuroscience, but also used in interpretability research. What would then be even more interesting, and this is work we haven't done yet, but we're just starting to sort of set up the pipeline for, is asking whether the same sort of sets of representations involved in tracking item locations seem to then be recruited or sort of transformed or passed on to whatever we think is doing the false belief representation. Because that would sort of establish that the representations in the model or the information in each layer of a model is sort of being passed through the model in a sensible way, that the information flow of the model actually sort of maps onto what our intuitive understanding of doing it the right way might mean. Whereas if it doesn't, then that sort of would count against that intuition. So I think there's a big question mark here so far. So to conclude, I really increasingly advocate here for what I think of as a coherentist approach in philosophy of science. Is this idea that rather than trying to derive things just from a sort of like foundational principle, you want to come up with a sort of mutually reinforcing, mutually supporting pieces of evidence, kind of like a bunch of different testimonials, using what I also think of as like a process of triangulation. Right? We know that we're not going to be able to necessarily formalize a definition of theory of mind for these models. It's probably going to be elusive. But if we can start to using theoretically motivated experimental design, right, we can start to triangulate the question, hopefully, through these different processes that I've talked about, right? Establishing converging validity across tasks, satisfying preconditions at appropriate developmental stages. Something we're still working on is this analysis of internal mechanisms. And I would say for the models we've tested so far, the picture is sufficiently incoherent that I would be very hesitant to draw any strong conclusion about like saying that they have theory, right? It's when they start to show really strong convergent validity, satisfy these conditions, in this developmentally sensible way, that you have to make sort of the stronger, or face a stronger question about whether you want to attribute theory of mind to them. And then the final thing I'll just say really quickly is which LLMs are we even talking about? So I sort of have a separate interest here, which is when we ask, do LLMs have theory of mind, what is the actual population of language models we're even talking about in the first place? Language models vary in their size and the amount of training data and the language they're trained on and their initial parameters. I have a general interest in sort of like what it means to draw generalizations from one sample of language models to a broader sample, or in this case to humans as well. So if we're thinking about using language models to model organisms, what are the kinds of constraints on the kinds of inferences we can draw from a particular language model or a sample of language models to human cognition? Thanks so much for listening. Thanks to my collaborators for all your work on this, and lots of conversations with people about all this work. And looking forward to hearing all your questions as well. Yeah, I think I saw your hand first.
Hi, my name is Scotch. I really like your talk.
Thanks.
I was waiting for you to mention mechanistic interpretability, and I was so happy to see it again.
Cool. Yeah.
So originally I was going to ask about that, but another question I had was about chain of thought reasoning,
Mm-hmm.
because it seems like it could be very valuable. I don't know if any of
Right.
these were reasoning or thinking models,
Yeah.
and it would be very interesting to see if there's also a correlation, a faithfulness between the chain of thought and the actual outcome. How do you explore that?
Yeah, great question. So yeah, I'll repeat it for the well, actually, no, there's no people on Zoom, so I don't have to repeat. But I will anyway, just to summarize. So first question on sort of chain of thought. Yeah, so sort of mixed feelings about it, just because. So for the question of using these systems as distributional baselines, I think it's less appropriate just because there's a lot of training that goes into getting them to do chain of thought that makes it less appropriate as a distributional baseline specifically. Because there's information that gets into the training signal, I think, that makes them not purely distributional baselines at that point. That doesn't mean they're not good model organisms for something else. But for the initial question I started out with, we were mostly interested in base models and used some instruction-tuned models just to see if there's a difference. I do think that chain of thought would help. And I do think we have an interest in looking at that. I know there's a lot of work, as you're probably aware, looking at like the faithfulness of chain of thought to the mechanisms. Yeah, I don't have a strong intuition as what you'd see there, but I can imagine that prompting a model to give like an explanation or to sort of show its work on its way to its answer would probably improve performance on this. Although I should also say that I could also imagine that if you design your stimuli in the right way, and I was talking to some of the people at lunch about this, there's a lot of work that's also come out where people perturb stimuli in certain ways in the theory of mind tasks, such that it looks like a canonical false belief task, but there's some important difference. So maybe the box is transparent, for example. I could imagine that if you design the stimuli in the right way, you might actually encourage the chain of thought to sort of bias you towards solving it in the canonical way, but actually it should be solved in some sort of alternative way. But I think that's a really interesting question to follow up on. Yeah, and I agree, looking sort of another example of convergent validity, I guess, is looking for convergence across the explanation the model is giving in the chain of thought, and also the whatever explanation we think we're doing when we look at the mechanisms in the model. So yeah, I think it's a good question. Yeah.
So the thing that I was most surprised by is that there were the differences were so great on why some models did better on some of the opinion tasks than others.
Right.
Do you have any ideas why the own OHM model did so well on the inference task compared to the others?
Unfortunately, no. I mean, that sort of speaks to this last thing I was talking about generalizability, which is like, we don't have a great theory at this point of that connects constitutive properties of the model, like how it is trained, what it's trained on, the size of the model, whatever you might think of as design properties of the model, and our predictions about its behavior. We're actually still pretty limited in that. The best we can say mostly are what they call scaling laws, so generally bigger models tend to do better. And we did see that across most of the tasks. It's just that it's not consistent enough to say, let me bring up the graph again. Like in general, the better models here are the models that are bigger. So if you look at the top of the distribution, they tend to be the bigger ones. It's just that it's not the order of the models, and their performance is not so consistent that you can draw a strong conclusion. I don't know. It's possible one good way to do that would be to do this kind of mechanistic work where you can look at the relevant circuits that seem to be involved in solving the task in each model, and see whether maybe they are more pronounced for certain tasks than other tasks or something like that, if they are not actually overlapping circuits. But we don't have a great hypothesis at this point, and I think that's actually a problem for the field in the sense that we don't know how to actually draw generalizations about a broader class of model beyond. We can just say this model did better than this other model, but of course with human subjects research, right, people, there's a sort of growing interest in the last couple decades in individual differences. So I think if you can try to identify some properties of the model that predict the performance, I think that's sort of the what we'd want to aim for.
Are they all trained on the same data sets? So
They're not, yeah.
Do you access, I don't know, maybe it uses the training set for for OM has more uses of the subjunctive tense? Or
Yeah.
something like that.
That's an interesting question. Yeah, I mean, another thing we've talked about doing really is fine-tuning the models on different kinds of constructions or mental state verbs and seeing how that affects performance. But you could also do a data audit and ask whether they see a higher ratio or just raw volume of mental state verbs or
Right. So
sentential complements.
He thought I would look versus
Right.
That kind of thing.
Right.
So train it to.
Yeah, no, I think that's a great idea. We do know, I think, we definitely know what Olmo was trained on. It's hard to do unless you need a specific hypothesis about what you want to look at in the data because it's just such a vast
Right.
training set. I believe Quen is also an open data, but it might only be open weight, in which case we couldn't look at the data for it. But I think that would be a good place to start. Thanks. Yeah.
And so, in particular, for getting at the question about whether the large language models have theory of mind in
Yeah.
a way comparable to humans or what we would recognize, it seems like you would really want to know about the convergent validity of your tests with humans.
Yeah, I
You
agree.
mentioned that
Yeah.
briefly in passing. But but it doesn't seem like that would necessarily be that hard to do if you buy the idea that autistic populations or certain kinds of them don't have theory of mind. That's a component part of the autism. Then we ought to be able to see whether on your 6 tasks people do some people do sort of equally badly on all of them, and some people do sort of equally well on all of them.
Yeah, no, I think so. Yeah, it's definitely a limitation, which is that we don't have basically you want a baseline correlation between all the tasks for humans. You want to know on average how much do these tasks correlate with each other for a human sample. I do think it would be possible to do. It's just that one challenge is just sort of cross contamination between the tasks. So if you give a person the indirect request task and also the false belief task, you might expect task dependent effects. If they already did the false belief task, that might prime them to solve the indirect request task in a certain way. So it would be hard to get sort of perfectly, whereas with the language model, each instance is sort of a fresh sample, but I agree, it's not impossible in principle. The one challenge or one thing I should point out is that within the theory of mind literature, there is a lot of debate about convergent validity already across tasks. And so, in fact, there are lots of people that would argue that theory of mind is not itself, it's actually a bunch of sort of discrete or distinct capacities that we're kind of measuring, saying as one thing, but actually there's this one task that's measuring one thing. And there's some studies suggesting that sort of false belief task performance in humans don't have predictive validity in children don't have predictive validity for how they sort of behave socially. I think that came out in the last few years. So it's a complicated question for sure.
It does seem relevant to what I would mean by the idea of a theory, which is some maybe axiomization of a system that makes concrete predictions or concrete.
Agreed. Yeah. And I mean, there's also just a case to be you could argue that the task we chose are not the right task. That's another question. Is should we have used a different set of 6 tasks or more tasks? There are at this point probably over 100 benchmarks that have come out in the NLP world on theory of mind. Many of them I would say are not great, but they are all kind of trying to get a similar question. That would be the kind of very data-driven approach if you just run the model on tons and tons of different tasks and hope that some of the difference come out in the wash. I tend
to think about it first.
Yeah, I agree. Yeah, I have more of a bias towards wanting to do it sort of in a theoretically motivated way. The best I can say with respect to sort of convergent validity across tasks is if you go back here, we actually haven't run the short stories task for all the open weight models yet because it requires a lot of coding for the individual free responses. But we do have data. So I mentioned this originally came from a study I published in 2020, this indirect request task. And what we found was that an individual human's likelihood of making a different interpretation based on what a speaker knew was predicted by their performance on the short story task. So that paper was basically correlating this mentalizing task, the short story task, with your propensity to take into account a speaker's knowledge state when you're doing a pragmatic inference. So we do actually kind of have one baseline here, which is the correlation between these two things. And I don't remember off the top of my head what the raw R correlation is, like the Pearson's correlation, but there's relatively significant, relatively strong. I think you had your hand up.
So just a quick question. So really good talk. But as humans, right, we have a theory of mind about other humans, and it seems like what we're probing is whether LLMs have theory of mind about humans.
Yeah.
Is there a way to maybe probe LLMs if they have a theory of mind about other LLMs?
Right.
And if do you think there's a way to maybe translating these tasks you have about human characters to be more LLM-like?
Yeah, that's interesting. Yeah, I mean, actually kind of speaks, I guess, to the question of what we think we're even measuring in the first place. So, like, on the one hand, I see the motivation for the question, which is like sort of familial theory of mind or something, but at the same time, a language model doesn't actually see nearly as much information about language models in its training data as it does about people. Like, the kinds of things that language models encounter are descriptions of people and why they did what they did, or just facts about the world. And so it's actually, I don't think it would be surprising that a language model should have sort of like better predictions about people than another. It's not even clear necessarily what it would mean to have theory of mind for language model. I do think there's a question about the reverse, which is human theory of mind for language models, which is sort of more of a human-machine interaction question, which I'm also interested in. But yeah.
I just follow up on this one. What kind of sense of self do you think an LLM has such that it could have a theory about another LLM?
I was thinking about, self and false belief trust, and I don't know, the only thing I could come up with is, we have an LLM, and it goes offline, and a rogue hacker, changes the database while the LLM is offline, and then you ask, where's the LLM for information online? So, according to possible, or is it not right away known that the information is good?
I think it's one of the issues, right, is they have a lot of training on human activity.
Yeah, exactly.
Humans do a lot of activities.
Yeah.
And LLMs only do one activity.
Yeah, so I was thinking, what if you take like another training from the LLM that knows pretty fresh neural network?
But yeah, this would imply, or it would require that they have a sense of self, a theory of their own mind.
Yeah.
And like you said, they're trained on human data, so whenever, before they put all these algorithms, these people play with this, they ask how what they think about themselves. And they would always pretend to be human.
Yeah, I mean, there is some work on what they call it introspection. It's sort of controversial to call this introspection, but the closest to the question of whether they have a sense of self is looking at basically whether an LLM can make accurate estimates about its own behavior. So, like, you could ask whether this kind of amounts to different ways of prompting it, essentially. So you can ask, in some cases, you can ask an LLM to predict its internal states. There's some research that came out from Anthropic a couple months ago, where you try to get the LLM to control its internal states. So if you say something like, think about a rainbow while you repeat this sentence, or don't think about a rainbow while you repeat this sentence, and then the LLM says nothing about a rainbow, right, because it's following the instructions. It just repeats the sentence that it saw. But if you look inside the internal states of the LLM, if you use like a sparse autoencoder to look at the concepts that the LLM seems to be activating, there's a higher activation of the rainbow concept. So lots of ways to interpret that, obviously, but one interpretation is that the LLM has some sort of that certain stimuli are able to sort of reliably elicit activations. Whether you'd say the LLM has control over that, I think it's an interpretive question, I think. The introspection question, I'm trying to remember how the typical experimental paradigm works. I think it would be something like asking a language model if it would assign a higher probability to one string than another string, or something, like a grammatical string than an ungrammatical string, and being able to see the degree to which, it's almost like an internal reliability question, like to what extent do its answers about its predictions about its behavior actually correlate with its behavior. Again, whether that's introspection is a separate question. But I guess the other fine point on this is, to what extent does that correlate more than its predictions about another language model's behavior. So like, to what extent does it have unique predictive insight about how it will respond to something than another LLM? And there's some evidence from the paper that came out last year that LLMs do have stronger correlations between their predictions about how they'll behave and how they do actually behave than how they think responds. Another LLM will behave and that LLM's behavior. So the self-prediction and behavior correlation is stronger than self-other prediction correlation, if I'm remembering the exact finding correctly. But yeah, follow up.
I do have another question. Because another thing I see people play around with is with classic puzzles or riddles, like the doctor riddle. And,
Right.
We will often get those right, but then sometimes people does it and invert the riddles.
Exactly.
It's just that they're no longer riddles.
Right.
And it's almost like the elements of an overfit.
Exactly, yeah.
As riddles. And so I wonder if something like that applies to false belief, if you tweak the false belief path,
Right.
so it's no longer actually a false belief path, but it looks like one.
I think, yeah,
You can fool them.
agreed, yeah. So I think that sort of speaks to this idea of like, when it's not quite data contamination, but we don't know whether it's generalization, because like they clearly have seen Sally intent, like it would be in other people. And so I think that's exactly the right intuition. There's this paper, I think I mentioned already, by Shapiro et al. Called like Clever Hans, or Neural Theory of Mind, or Clever Hans, or something, I'm getting it really wrong. Where they do kind of exactly this idea, like making the box transparent, any kind of perturbation to the situation. Tumor Ullman also has a paper.
I think it's like with Sally, migrator or something like that.
Right.
Are they going to, because they overestimate, I think, what Sally will know, right? They err in that direction that she should know.
Do they overestimate? Let me see.
Was that the original finding, was that they...
You mean for the results I presented?
And they are erring on the side of, she'll look in a place that she shouldn't know.
Let's see. I think that's probably true. So yeah, I guess on average, I think log odds are negative, which means that it is generally more likely to think that Sally will look in the correct location. So I think that's consistent with what you were saying. If I'm
biased in that direction, but
yeah.
you're pushing too far, like,
Yeah, right. I imagine you could. But then I think the question is, you definitely want a human baseline, because in all these cases you want to know, would humans also be biased in the same direction? Are humans also doing like a Clever Hans kind of thing on the same task? But yeah, I think that's exactly the right kind of question to ask. Yeah.
Thanks. So, given your critically reasonable remarks about triangulation at the beginning, wonder how you can apply to somebody who goes back to the beginning and said, you have a thing I think was called like axiomatic regression.
Yeah,
Which of course sounds harsh.
Yeah.
But now imagine somebody who says, how about triangulational skepticism? Lots of social animals out there without language. Some evidence from broadly Thomas and company that humans' ancestors have a heightening of theory mind capacities in other primates. Work out of, call it, Lyle Lightman and his students, that even if you suppose the 2-year-old has a massive theory of mind, you still have a nightmare explaining how they acquire any words at all.
Right.
So start thinking maybe theory of mind is language independent.
Right.
And in fact is a precondition for acquiring a large lexicon. Each of those pieces wobbles.
Yeah.
But if we're thinking convergent and triangulationally, then if somebody comes to the talk thinking, oh look, I know there are people out there thinking based on training machines in the next word, like magic is going to happen inside. Right. But like Freddie Pico did magic, had like some story about how training on the next word. Like if somebody said, hey, training on the next word, you actually know about really quantum physics. Like, maybe.
Right.
Probably not without reading articles on quantum physics. Right. And so likely if somebody says maybe by training on the next word, these things hit on that which we share with gorillas and horses amped up a bit. Wow. And absent a story of how, then what would be applied to somebody who says, yeah, like very, very deep skepticism that whatever they're using to answer the question, yes or no, is just a very, very different thing than our version of refinement?
Yeah, no, I think that's a great question. There's a couple of things to pull apart there, I guess. One is, it depends what question you're answering. So I think it could totally be the case that the substrate or sort of causal mechanisms responsible for human fluid mind are distinct, and it could be the case that the element still has theory. So I think they're kind of distinct questions. Like, I think what this epistemic mode is doing basically is like demonstrating the sufficiency but not the necessity of language. So it seems totally possible that language could be sufficient but not necessarily, and thereby maybe it's sort of multiply realizable computational.
So then, is the question sufficient for what? See, I could totally believe that enough data will be sufficient for having some mechanism that answers yes, no to the theory of mind those questions in a way that begins to match human behavior.
Right.
And if that's what we mean by theory of mind, then I'm like, sure. But then I'd be guessing that maybe the things we're calling theory of mind are so radically different over the period that not a whole lot is gained by calling them all theory of mind. Unless you just mean, what I mean by theory of mind is having this disposition to be able to answer theory of mind questions. But if I need more than that, I was thinking there was some natural capacity that the 2-year-old has, that some heightened capacity of finite theory of mind, which might be some heightened capacity of a much older. If that's what I'm after, like, what natural capacity is it humans are throwing at, let's say, acquiring lexical items and then later answering theory of mind questions on the hope that there's some similarity there. Then I guess the question would be, is there antecedent reason for thinking that the time training these machines go through is going to get them there? Granted, it's totally possible that it gets them to have some disposition to answer theory of mind questions.
Yeah, I mean, I think there's a little bit of, so like the question of whether there's a natural capacity, it feels like that already kind of assumes, or how the natural capacity gets there seems like that assumes there is a natural capacity, right?
That's what I said. Like, so if one was thinking triangulation gets you there.
Yeah, right. Yeah, I see. So if you say you have a triangulation-based account of there being a natural capacity versus a triangulation-based account of the behavior that we think is consistent with the capacity. Yeah, no, I think it's a really good question. We need to about that. But I mean, I think it is a totally viable response to say that whether you call axiomatic rejection or triangulation-based rejection or skepticism, that if your prior is strong enough that the mechanism or the system responsible for your mind in humans is not driven by this like language, but that it must be shared with it's the same mechanism you see in non-linguistic primates, for example, then I think it's totally reasonable to say that we don't think that the evidence that a system exposed to language could display the same behavior would be demonstrated through the mind. I do think that should then hone the question of viability of the test, because and so maybe you could make a differential conflict earlier, but I think if you're in the axiomatic rejection, then now you have a system that you don't think has the mechanism, but it's passing the test that's supposed to test the mechanism, and so then I think you have to decide whether you think the test is actually picking up on the right thing. If I'm understanding correctly, or you're saying that there's some possibility that the same behavior, maybe you're actually more of a differential conflict theory camp. Is that fair? Oh.
We're over time. But I'll remind everyone that there is the reception in the playroom A1 through 9, which is where we're all going to go. And so if you have more questions, or if you want to keep hearing Paul and Sean talk about this question, I'm sure we can continue that. Thanks, our speaker.